Okay, so hi everybody. I want to thank the organizers for allowing me to give the talk by Zoom once I wasn't able to make it. I'm going to talk about multiplicative extractors for sampleable distributions, and this talk is dedicated to the memory of Luca Trevisan. So this is a talk about extractors. So we all know the motivation for randomness extractors, mainly how do computers get random bits. And let me review the standard definition of extractors. So extractors come in two flavors. There are what are called seedless or deterministic extractors and seeded extractors. And in this talk, I'll be talking about seedless or deterministic extractors. So a seedless extractor is a function which is able to extract randomness from a weak source of randomness. So the scenario is that we have a weak source of randomness that is available to computers. Somehow computers are available to sample some distribution from nature. And we want to extract pure randomness, namely unbiased and independent random bits from this distribution, and the definition is as follows. So a function x from n bits to m bits is a k epsilon extractor for a specified class D of distributions of allowed weak random sources if for every distribution x in the class that has sufficient mean entropy, that the mean entropy is at least k, where k is a parameter, the output distribution of the extractor is epsilon close to uniform, where distance is measured by statistical distance. So this is a standard definition. This is what is known as a seedless extractor. And people who know about these things may be familiar with seeded extractor. A seeded extractor is a similar object, but here we allow the extractor to get an independent seed of truly random bits in order to extract randomness. And the advantage of seeded extractors is that once we allow this additional seed, then we don't need to bother with the specific class of allowable weak random sources, because seeded extractors are able to extract randomness from the class of all distributions, or all sufficiently high mean entropy distributions. And because of that reason, even though historically seedless or deterministic extractors were considered first, they were mostly abandoned in the 90s because the classes of weak sources that were considered in the literature at that time required a lot of structure, and they were deemed as unrealistic for modeling the kind of distributions that are available to computers in real life. And then in 2000, there was a very influential paper by Trevisan and Vadan, and they wanted to return to seedless or deterministic extractors. And they wanted an extractor, they wanted to define a class of distributions which captures the kind of distributions that are available to computers in nature, which avoids structure, right? So it not assume strong independence conditions between sources, and allow seedless extractors that run in polynomial time. And their intended application was selecting keys for cryptographic protocols, which is maybe the most adversarial scenario in which we want to extract randomness from weak random sources. And the class they decided upon is the class of samplable distributions. Here I'll talk about distributions which are samplable by polynomial size circuits. So what is a samplable distribution? A distribution X is samplable if there is by a certain circuit, if there is a circuit A, such that if we feed A with uniform random bits, it outputs the distribution X. So it's right in the standard definition of what is known as efficiently samplable distributions by circuits. And let me denote by samp S the class of all distributions which are sampled by circuits of size S. And Trevisan and Vadan made the following philosophical claim that, that nature must be efficient, namely that sources that are found in nature and are available to computers should be efficiently samplable. So this class of sources should cover the distributions which are available to computers, even if we consider circuits of small size, say linear size or quadratic size. But then Trevisan and Vadan immediately noticed that any extractor for distribution sampleable by size S circuit does not have a circuit of size S. And this has two conclusions. One is that if we want explicit extractors, namely extractors that run in polynomial time, the best we can hope for are results of the following form. For every constant C, there exists an explicit extractor for distribution sampleable by size n to the c circuits, but this extractor will run in time which is polynomial, but the polynomial will be larger than n to the c because the extractor does not have a size n to the c circuit. So that's the first thing. And then, even if you like such results, then the existence of such an explicit extractor implies circuit lower bounds. And of course, we don't know how to prove circuit lower bounds. So the best we can hope for are conditional results, or what we like to call hardness versus randomness trade-offs, namely results of a form, give me a circuit lower bound, and I'll give you an extractor. Okay? And indeed, the main result of Trevisan and Badan in that influential paper was that under a suitable hardness assumption, under a certain circuit lower bound, which I'll state precisely in a moment, we have a result of a form which I just described. Namely, for every constant C, there exists an explicit extractor for distribution sampleable by size n to the c circuits with the following parameters. The parameters are not that important, right? But let me just say that the mean entropy is rather high, and this is a problem, but I won't talk about it in this talk. The output length is fairly large, which is good, and the error, how close we are to the uniform distribution, which will be the focus of this talk, is small, but not as small as we'd like. It's only 1 over polynomial, whereas we would probably want it to be smaller, to be negligible, or maybe even exponentially small. And now let me tell you about the hardness assumption which Trevisan and Vadan used. So this is a template of hardness assumptions where we say that the class E is hard for exponential size circuits of type X if there exists a problem L in the class E, namely d time 2 to the O of n, and a constant beta, such that the class L cannot be computed by circuits of a specified type of size 2 to the beta n. Right? So this is a template of assumptions. It depends on what type of circuits you take as type X. And this assumption was popularized by Impagliazzo and Wigderson in 1997 in their celebrated work showing that BPP equals P if you assume this type of hardness assumption against deterministic circuits, right? So if the type of circuits you are considering is deterministic circuits, then under this assumption, BPP equals P. Now, Trevisan and Vadan wanted to construct extractors for sampleable distributions, and they only knew how to do it using a much stronger hardness assumption, the same type of hardness assumption, but not against deterministic circuits, but rather against what is known as sigma 6 circuit. Now, what is a sigma 6 circuit? A sigma I circuit is a circuit which, in addition to the standard gates, is also allowed to compute a complete language in sigma IP, namely NP to the MP to the MP to the MP, right? I mean, polynomial time hierarchy I times. So we're assuming hardness against much stronger circuits, a form of non-deterministic circuits, or maybe even several higher in the hierarchy. So this is a very strong and yet plausible assumption. So this is the celebrated result of Trevisan and Vadan. And for many years, there was no progress on this problem until 2 years ago in a remarkable paper, Ball, Goldin, Dachman, Soled, and Mutreja gave the following result. They showed an extractor with the same parameters, the same conclusion, but under a weaker hardness assumption. More precisely, rather than assuming a hardness assumption against sigma 6 circuits, they assume the hardness assumption against non-deterministic circuits. So not the same assumption as in Pagliazzo and Wigderson, but an assumption which is by now considered quite standard. It's been used in many contests and by many works. So this is a big and important improvement, but we still got exactly the same result. They use the same construction as Trevisan and Vadan, the exact same construction, but their proof is significantly more complicated in order to use this weaker assumption. Okay, so what are the results that I'm going to tell you about in this paper? So the first result I'm going to tell you is a simpler proof of the work of Ball, Goldin, Dachmann, Soled, and Mutreja. And I would actually argue that it's even simpler than the original proof of Trevisan and Vadan. And here I should say that we get the simpler proof in the case that I told you, but the BGDM paper also gets extractor for quantumly samplable distributions. That's a different model that I'm not going to talk about. And the new proof technique that I'm going to show you is not going to get that, but a simpler proof of this theorem. There's also in the paper a partial justification for the necessity of hardness assumptions for non-deterministic circuits, at least for the kind of proof techniques that we use in these papers. Maybe I'll get to say something about it later on. But the main thing that I want to emphasize is this word multiplicative. In the title, the extractors that we construct are multiplicative, and I'm going to try to sell you the notion of multiplicative extractors, what they are, why are they interesting, and why should you like them. Another comment is that our extractor, this multiplicative extractor, is a component in the subsequent work with Ball and Silbach, which achieves lower mean entropy, and maybe I'll get to say something about subsequent work at the end, right? But right now, what I want to focus on is that we get the same result as BGDM, with the advantage that the extractor is multiplicative, and I want to explain what multiplicative is. So here is a slide trying to sell this notion of multiplicative pseudorandomness. So in order to do that, let's review the standard definition of pseudorandomness that we all know and like. So we say that the distribution Z on 0, 1 to Vm is pseudo-random against a class of functions from 0, 1 to Vm to 0, 1. And the classes that we typically consider are the classes of polynomial size circuits, or maybe sometimes we consider the class of all functions when we talk about statistical distance. So we say that the distribution is pseudo-random against the class C, if for every function C in the class C, for every potential distinguisher, when we consider two experiments where in one we give the function the uniform distribution, and in the second we give a function the pseudo-random distribution, and we measure the probability that these in two experiments that the function answers one, then we want these two quantities, P1 and P2, to satisfy the following relation, namely that P1 and P2 are close. And I'll call this relation the additive relation, right? So that's the way we usually define pseudo-randomness. Now, in the examples of classes that I gave you, polynomial size circuits or all functions, these classes are closed under complement, so I don't need the absolute value, and I'd rather omit it and replace this condition by the following condition without the additive, without the absolute value. So two numbers are close if P2 is smaller than P1 plus epsilon, right? And now, inspired by differential privacy, we can choose other relations between two numbers for measuring closeness. So if this is an additive relation, maybe we would like to use a multiplicative relation. So for example, in differential privacy, they use this following multiplicative relation where two numbers P1 and P2 are close up to epsilon. If P2 is not larger than e to the epsilon times P1, so think of e to the epsilon as 1 plus epsilon, right? I mean, this is roughly true. So this is a multiplicative notion, that P2 is less than P1 times 1 plus epsilon rather than P1 plus epsilon. And another relationship that is considered in differential privacy is one where with two parameters, a multiplicative parameter, epsilon, and an additive parameter, delta, which we typically think of as much smaller than epsilon. And here it's the same multiplicative relation, P2 less than e to the epsilon times P1, but we also allow this very small additive parameter. Okay, so why do we want to allow these new relations? So the motivation, just as in differential privacy, is that if it is sometimes impossible or very expensive to get pseudo-random distributions with very small epsilon, then we get a stronger pseudo-randomness guarantee for the larger epsilon that we can afford if we use multiplicative or weak multiplicative pseudo-randomness. And this is because the multiplicative relation is stronger than the additive relation, right? Whenever the multiplicative relation holds, the additive relation also holds. But in fact, in the special case where P1 is small, you can see that 1 plus epsilon times P1 may be much, much smaller than P1 plus epsilon in the special case where P1 is small. And I'm going to give an example in a moment. So the basic idea is that by strengthening the notion of pseudo-randomness, taking a multiplicative relation instead of an additive relation, we can get a stronger guarantee for a larger epsilon, and hopefully this will be helpful. And a multiplicative extractor is an extractor that is defined with respect to the multiplicative relation rather than the additive relation. So let me spell this out. So this leads to the following definition. This is from a paper with Artmenko, Appelbaum, and Young. We say that an extractor, deterministic or seedless extractor, is multiplicative if the output distribution Z, namely x of x, satisfies the following multiplicative relation. For every event A, the probability that the output is in the event A, the output of the extractor in the event A, is less than 1 plus epsilon times the probability that the event A under the uniform distribution. So rather than adding epsilon, it's 1 plus epsilon times that. And it's very easy to observe that this definition is equivalent to saying that for every possible output string in the distribution of the extractor, we want that the probability that the extractor outputs this string is less than 1 plus epsilon times 2 to the minus m. And recall that the extractor outputs m bits, so 2 to the minus m is the probability under the uniform distribution. Okay, so that's a definition of a multiplicative extractor, this stronger condition. And now I'm ready to tell you, right, I mean, what is the main result? So the main result of this paper is that under the same weak assumption used by the BGDM paper, if E is hard for exponential size non-deterministic circuits, then we get an extractor with exactly the same parameters as the previous work by Trevisan and Vadan and BGDM, but now we have the added benefit that the extractor is stronger, it's multiplicative rather than additive. Furthermore, if you want to push the output length to be larger, not just omega of k, but very close to k, then I can do it, but then I can only do it if for the weak multiplicative relation, where I get an extractor with a weak multiplicative relation, where the additive parameter delta is very, very small, exponentially small as it should be. And let's just recall that the weak an extractor is weak multiplicative if here we add this plus delta. And once we add this plus delta, we lose the equivalence with a nicer definition that only talks about individual output strings, and we return to the definition that I showed you in the previous slide, right? So this is the main result under the same hardness assumption as in BGDM. We get an extractor with the same parameters, but now it's also multiplicative. Okay, but why should you want multiplicative extractors? So now I'm going to make the point that multiplicative extractors are in fact much more suitable for the original application considered by Trevisan and Vadan, that is sampling keys for cryptographic protocols. So the motivation of Trevisan and Vadan was that we want to use these extractors in order to select keys for cryptographic protocols. So more specifically, say that there is some protocol that uses an m-bit random key, and it is secure in the case that the key is uniform. So let's say that it's secure in the sense that if we define the event that the adversary cheats, that the adversary can steal the honest party's money, then when the key is chosen according to the uniform distribution, the probability that this event occurs is very small. It's smaller than some alpha, which is negligible, n to the minus a little omega of 1. So the probability that this protocol is secure. Now, if we don't have access to true randomness and want to use a weak random source and an extractor, and if we use the standard definition of an extractor, an additive extractor, namely we choose the key by sampling an element from the weak source and applying an extractor, we'll call this distribution Z, then the standard definition of extractors, the additive definition, only guarantees that the probability that the adversary can steal the honest party's money is less than alpha plus epsilon, so it's really epsilon. And now the question is, how small can epsilon be? And in the results I showed you earlier, epsilon was small, but not very small. It was only 1 over a polynomial for a fixed polynomial. And in fact, in that paper I told you, but with Appelbaum, Artmenko, and Young, we showed that in some precise sense, black box techniques, the kind of techniques that we use to construct extractors for samplable distributions from hardness assumption, cannot give explicit extractors with small error. So we have to have large error, and this means that we can never get negligible epsilon, and additive extractors do not suffice for the application of selecting keys for cryptographic protocols. But now here comes multiplicative extractors to the rescue, because now that we've changed the definition to this multiplicative definition, then if we use a multiplicative extractor, then the probability that the adversary can steal the honest party's money is now 1 plus epsilon times alpha, 1 plus epsilon times what it was under the uniform distribution, and this is very small, even when epsilon is large, even when epsilon is half. And in fact, just like in differential privacy, even when epsilon is 10, right? So even though, it's sufficient to get multiplicative extractors with relatively high error in order to use them for these particular applications. So multiplicative extractors do give negligible chance for the adversary to fool the honest party in this application, and they do suffice for selecting keys for cryptographic protocols. And in fact, by the same rationale, even the weak multiplicative extractors with exponentially small additive parameter delta, for the same reason, suffice for the application. This is the reason I defined this notion and was interested in constructing it. Okay, so the bottom line of this slide is that for some applications, multiplicative extractors do better than additive extractors, and specifically for the signature application of selecting keys for cryptographic protocols. Now let me tell you a little bit about the proof, and really just a little bit. So unlike a previous work by Trevisan and Badan, the BGDM paper, which constructed extractors for sampleable distribution directly from the hardness assumption, we'll use an intermediate object. Namely, we'll do the construction in 2 steps. Specifically, we'll start from a hardness assumption against non-deterministic circuits, and we'll end with an extractor for samplable distribution, but there will be an intermediate object, and this intermediate object is going to be a seed-extending pseudo-random generator for non-deterministic circuits. So it's a pseudo-random generator that pulls the class of a small non-deterministic circuits with a twist that I'll require this pseudo-random generator to be weakly multiplicative. Namely, for every non-deterministic circuit D of size n to the c, I'll want that the probability that D answers 1 on the pseudo-random distribution is less than the probability that it answers 1 on the uniform distribution times 1 plus epsilon plus an exponentially small additive factor. And the point is that once you come up with this intermediate object, then showing that this object implies an extractor for samplable distribution is very easy, and you immediately get that your extractor is multiplicative. And then, once you realize that, in order to construct this weak multiplicative seed-extending pseudo-random generator from the hardness assumption, we use essentially the same construction as in the previous paper, but this turns out to be much easier to analyze because now we only need to analyze it on the uniform distribution, because pseudo-random generators are only measured on the uniform distributions, whereas if you want to analyze it as an extractor for samplable distributions, you have to analyze this on every samplable distribution with sufficiently high mean entropy. And this causes a lot of complications because the components that are used in this construction are more suitable to work on the uniform distribution. Now, since I'm essentially out of time, I'm going to skip the proof. I was going to show you the easy step. I'm going to skip it. But since it takes half a page, maybe you are somewhat convinced that it's easy. And let me conclude. So what did I tell you about? The result is the multiplicative extractors for samplable distributions. We use a weak hardness assumption against non-deterministic circuits. A multiplicative extractor is an extractor where the probability that the extractor outputs a fixed string is less than 1 plus epsilon times 2 to the minus m. And as is the case in the previous works, we only get extractors for large mean entropy. Another thing that I didn't tell you about is a partial, that is in the paper, is a partial justification or maybe just an excuse why we use hardness assumptions against non-deterministic circuits. But in fact, this excuse is maybe not as strong as it was, as we now have new techniques. This is in a joint paper with Justin O that bypass the limitation. And let me use the opportunity to also mention some subsequent work. So there is subsequent work with Ball and Silbach, and also this paper I told you about with Justin O, which gets extractors for lower mean entropy, which I think is a very interesting open problem. Most of these extractors are additive and not multiplicative, so it's an interesting open problem to making them multiplicative, and hopefully with the best possible parameters and under the weakest possible assumptions.
Ronen. That's too bad. Oh, Ronen, we missed you for the past 30 seconds. But do you hear us?
Yeah, it's probably my fault. It's my connection.
Okay.
So, right, I mean, so I was just saying that, yeah, whatever. Right, I mean, I'm probably out of time.
So let's thank Ronen.